Hi, I'm Dr. Laird, and the bit that I normally do is called Ask Dr. Laird Your Stupid Astronomy Questions. Okay? The problem with that bit tonight is there's hardly anybody in this room. So the chances of you asking any decent stupid astronomy questions is pretty slim. So I'm going to change it up tonight. I'm your resident stand-up astronomer, and what I'm going to do for the next 7 minutes is teach you special relativity and general relativity in 7 minutes. Matt, I'm going to need you to every now and then, when I'm failing, to say, tell me more. Okay, Matt? Every now and then, when it seems like I'm going nowhere, say, tell me more.
Okay.
Okay, thanks. All right. So, special relativity, we need two assumptions, both of which are true. First one is you are the center of the universe, which means that...
Amen.
No screaming, I need to get through this, okay? And the second thing is the center of the universe means that everything that is true for you is true for everyone else also. So that's the thing. Second thing is the speed of light is constant, which means that when you measure the speed of light, you get it right. Also, everyone else in the universe gets it right. Okay? Speed of light is constant. I'll leave it at that. Now, first thing is special relativity. How do we do it? Very simple. You're traveling in a very fast-moving spaceship, and it's going like this. Okay? You have a clock on where you are, and that clock measures time by having a light ray go up, down, up, down, up, down, up, down. And the guy in the spaceship, who's also the center of his universe, has no knowledge that he's moving with respect to you. You can see he's moving, but he doesn't know he's moving any more than I think I'm moving. Okay? So he's got a clock that goes up, down, like that. Okay? Now I'm watching his clock, and his clock, as far as I'm concerned, because he's going like that, is not going up, down, but is going like this. It's in a triangle sort of thing. So his clock, which as far as he's concerned takes 1 second up and 1 second down, from my point of view, because the speed of light is constant, it's taking longer to go up, down than he thinks, which is 1 second like that. So for me, I'm seeing his clock is moving slower. So we just did time dilation for special relativity. Also, in special relativity, we have things shrink as you go faster. Well, what is he doing? He's going this way really, really fast. But you know what? As far as he's concerned, he's getting somewhere really, really fast. And how does he do that? What he sees is things are shrinking. So that's how he can see that he can get somewhere very fast, because things are really shrinking, and that's how we can do it. Okay, we just covered special relativity in about 2 minutes. We're up to general relativity. Did everybody get it so far? Applaud if you understood anything I just said. Okay, good, very good. That's very good. Okay. All right, general relativity, one more assumption, okay? Einstein called it his happiest thought. It's a very simple thought, but it isn't intuitive. You have to be Einstein to get it. Nevertheless, here's the thought. Einstein said, if you're traveling in outer space and you're just traveling along all the way away from everything and whatever, and you're traveling at a constant speed and you're floating in that spaceship, that's what you feel like. But guess what? You can't tell if you're in an elevator, which is simply falling to the ground like that, and you're also floating in the elevator. So you can't tell the difference between free floating in a gravitational field, which is pulling you down, or being happily moving through empty space. You can't tell the difference. Now you have to buy that. It makes some degree of sense because you've been playing with, stuff in outer space for a while. But to Einstein, it was a great idea. You can't tell the difference because there isn't any difference. So there's no difference between falling in a gravitational field and going straight out into the universe in the absence of any. Okay? Now, if you like that assumption, which is in fact true, it's not an assumption, it's true. So if you like that one, now this is how you prove that space-time is curved. We're going to do curved space-time in the next minute and a half. Okay? Yes. Are you ready for that? Yes. Curved space-time, and so we're going to eliminate. We're going to eliminate gravity, because gravity doesn't pull on you; it just curves space-time. So here's how you can prove curved space-time. I'm in a spaceship in outer space, moving away from everything. All right, and I throw a ball in this direction, and I catch it with this hand. I throw it from this hand. I catch it with this hand. It goes straight. Anybody disagree with that? No, of course not. Newton said you throw things that go in a straight line. Newton said that. It's still true. Okay, now, I'm in that spaceship, which is floating in gravity. I have only 1 minute left. And now I'm in the gravitational field. So the gravitational field is pulling me down. Now, in the falling spaceship, I see it going straight, just like everything else ever did. But guess what? The people on the ground, they see the spaceship go down. So when I throw the ball, which should go straight, I actually don't see that, because the place where it's going to hit is now lower than it used to be. So when I throw the ball, the thing that I see goes down, in spite of the fact that the guy in the spaceship sees it going straight. And why do I see it going down? Because space-time is curved. And that's why a ball goes around the Earth, because space-time is curved. And I just proved to you that space-time is curved by gravity, but it doesn't pull on you, it curves space-time. I did special and general relativity in 7 minutes. That's a world record. I am Laird, Dr. Laird Whitehill, your resident stand-up astronomer. Thank you very much.